Hello, everyone, and welcome to the Geek Narrator Podcast. I am back with another episode, and today we are back with another database called XTDB. And I have today Jeremy and Malcolm from Juxt, and we are going to talk about XTDB, its internals, its architecture, some of the use cases, and give you guys insights about the database. So, welcome, Jeremy and Malcolm. I'm really excited to have you both. And
Hi.
let's start with the introduction.
Great, yeah, great to be on. So, my name's Jeremy Taylor. I've been with Juxt for 5 years. So, Juxt is a consulting company. So, it had its main focus and background in the Clojure ecosystem, but also has a lot of experiences in financial services. My role joining Juxt was to take this open source project that we had it was actually called Crux at the time, and figure out how we can commercialize it and work with our open source user base and early clients to turn it into a product. My role as head of product is to do everything that isn't strictly core development on the database. I did join as someone that was very keenly interested in Clojure, which is a functional Lisp that runs on the JVM. But day to day, I'm more looking at where we should be taking the product and helping our users to adopt it and figure out those target use cases where it really shines. So yes, a bit about me. I guess over to Malcolm.
Yeah, I'm Malcolm Sparks. I'm the CTO and co-founder of Juxt. And I guess I could call myself a Clojure developer, really, amongst other things. And Juxt got going around 2012 and born out of the London Clojure community. And I have a background in databases, and I was used to be an Oracle DBA, and then Java arrived, and I latched onto Java. And so I met Clojure through going through a lot of Java programming. And then the company it's based mostly in the UK. We've had a tradition from the very early days of just writing stuff and libraries on GitHub and open sourcing everything that we can. And so often that is after a project that we were working on, and we reflect and think, wouldn't it be better if we did this as a library? And so the Clojure ecosystem is full of those sort of things where people write a small library to do one thing well. And so a lot of what we've delivered on our GitHub is, I think we're about to 70 or 80 repositories now that are open. But XTDB was one that was a little bit more serious. I think we attempted to write something much more ambitious, but still open source on GitHub. But this time it's in the XTDB organization, not the Juxt one. So it's a different organization because there's quite a few projects and sub-projects for XTDB, so you can go and find it.
Perfect. Yeah. Welcome. And I'm really excited to go deep and understand how it all works. Before we do that, talking about so many databases to so many different people, I've definitely realized one thing, that writing databases is tough, right? So why write another database?
So I think the shortest answer is that we haven't figured out how to build databases really. As a collective of software developers in industry, we've not figured out the most general ways to leverage the hardware that exists. What we call databases, for the most part, are very general purpose systems. And even if you're looking at a time series database or something which has slightly more optimality in certain contexts, there are always going to be ways that people want to use those where you have to break it apart or do something that's even lower level and bypass this more general purpose system. So I think that is a symptom of us not having the right software abstractions and having these monolithic general purpose systems that are slightly too complicated to extend and tweak, and then people have to break out of these siloed boxes. I guess what we're in search for as a company, group of developers working on this, is can we build a simpler system that's still general purpose, but more flexible and extensible? So that's very much part of our vision for that. I don't know if you have anything to add to that, Malcolm.
Only to sort of say there are two theories of the IT industry. There's one that says we're pretty much finished. We've done everything that needs to be done. Everything is all about a few optimizations and tweaks and a little bit of superficial stuff. Or you might take the view that we've just got started and everything is up for grabs and we've only scratched the surface of what is possible. And I'm certainly in the latter camp. And I've seen certain things in my career that have absolutely changed the game. And I would point to things like being able to network PCs together and get them to talk to Unix computers. That was a bit of a game changer. Things like distributed version control, garbage collection, things where it was something the industry was really struggling with, and then something comes out or like the World Wide Web, or those technologies, and then that's a game changer and we will move on. So I think there's so many different potential inventions that will progress us forward, and most of them are still yet to be discovered.
Okay. So I see that you mentioned a few problems with the general purpose database. Since it's general purpose, it tries to solve everything, but none of them in the best possible way. And then there you talked about abstractions and also the complexity part of it. So could you share some examples or probably experience working with the general purpose systems, and what are the challenges that you would like to highlight?
Yeah, so I think we very much come from this school of thought, which is really started with Rich Hickey. He created this language closure, and it really emphasized the idea of data as a first-class thing, which is independent of programming, the programming language. And as a result of that, he came up with this vision for Datomic, which was a database released just over a decade ago. And it really extolled this vision of what if we made some fundamental missteps with building general purpose databases by treating them as places where you can put things and pick them up again and take things out, change them, put them back. And having this sort of place oriented view of data storage was actually a really bad idea. And I think throughout the database community, we've seen the rise of immutability being really important at a foundational level, whether that's in LSM trees or just the way we treat object storage. And I think what Rich was arguing, has been arguing for well over 15 years, is this view where immutability shouldn't just be something that's within the system. It should be exposed to users, and we should be thinking about data as a first class thing. And he has this expression, database as a value. And if you look at that vision versus what, say, Postgres offers, where the update semantics in SQL in Postgres follow to the letter exactly what was described 50 years ago when hard disks were measured in the megabytes, if you're lucky. And the whole premise around update is that you destroy the previous version of the data and you mutate this record in place. And so the whole way of thinking about a general purpose information storage system, if it's based on SQL, is usually full of mutability. And this is, in our view, a mistake, or at least it's a very common problem that everyone has to work around time and time again. And it's a tax on the industry. So what we're looking to do with XTDB is to avoid common pitfalls that developers make when they are building systems against mutable storage layers, whether that's forgetting to implement soft delete appropriately or having to manually move data from a live table to an audit table or history table. And all of these very subtle but tricky design and schema problems which crop up all over the place. So my own personal experience is in e-commerce. So before Juxt, I was working on e-commerce systems where there were DB2 systems with hundreds of tables for all kinds of things. And a good subset of those had updated created version columns on each of these tables. And the amount of code that was generated and required to maintain a huge amount of version history just to ensure that business users were able to press undo, it was crazy. And so my view in all of this is that what if there was a more universal way to have undo across a database, and also then to think about how we version records in a first class way that doesn't involve a developer starting just with a raw update or delete in SQL.
Yeah, I think it's right. Jeremy's right to look back at Rich Hickey's programming language, which was Clojure. And I will just explain what Clojure is for maybe some listeners who've not heard of it or don't know its key features. Clojure is a Lisp, but it's not unique. In fact, there are lots of other Lisps, and it runs on the JVM. Its key innovation was that, and I can explain this in terms of a JavaScript object, because most of us know JavaScript. So in JavaScript, if you were to set a property on JavaScript, that property is set globally for anyone else who can see that object. They will see that change, and you'll lose the old change, and you can protect against that mutation. But in Clojure, the equivalent of changing an object like that is that you get a new version of that object. A little bit like doing a Git commit or doing a change in Git, you do a commit and you can go back to the old commit. So it's protected the previous snapshot. And when you have that ubiquitously throughout your language, you get some advantages. Like you don't have to lock objects because you can just snapshot them, and you know that they'll be protected from any update. So you don't have to lock them for mutation. And so then you don't have to distribute your locks. And working in a language like that, you just see it trains you to understand how much more reliable and how much nicer it is when when that feature is done and you can guarantee it, and it's done through every single library and every part of the ecosystem except for some of the Java interop libraries. But on the whole, it's guaranteed. It's a property invariant of the system. Now, when you then look at the world of databases, you just see lots of uncontrolled mutation. And as Jeremy points out, there are lots of strategies that you can have in database modeling to make sure that you don't lose old data when you update it. However, those strategies are ones you have to implement yourself and maintain yourself. And it turns out that those strategies can get very complex across a large number of tables. So wouldn't it be nice if we could bring this guaranteed invariant from the closure language and apply it in something much more important, which is a database, the records that we're going to keep forever?
Yeah, so sounds very good. And while you were explaining some of the problems, I could recollect some of the experience I have had working with general purpose mutable databases. There is so much context and so much application level logic we have to maintain just to guarantee that on top of a general purpose database. Sometimes it really gets complicated, and the more code you have to handle just that, it's a liability, and you're not actually able to focus on the core business logic or the core business problem you're trying to solve. So it's definitely an interesting concept, but I would also like to understand the trade-offs with that comes up with implementing immutability. But before that, I think let's start with understanding the what part of XTDB. What is it? Like, it's a database. We've talked about immutability. We've talked about like maintaining a version. But what is it? And so if we talk about the broad classification the industry has given us, like SQL database and NoSQL database, would you classify XTDB as a SQL database or a NoSQL database?
So that's an easy one to start with. So we've spent the last 3 years building a SQL engine essentially from scratch. So we chose not to use Apache Calcite or Apache Data Fusion. We took this sort of SQL grammar as declared by the standards body and have a version of that which parses and plans and optimizes entirely on our own stack on the JVM, mostly written in Clojure. And yeah, so that means we have a first-class SQL experience. And we did that because we wanted very fine control over the way the schema evolves. This is quite a big difference where you have a system that remembers everything. You don't have immutable schema either. So the schema has to accrete. And when you want to roll back or like view as of the past, you need to be able to also see the past version of the schema at the same time. And actually, this is quite a tricky problem in general. Often systems will resort to copying entire tables or versions of the database if they need to have both immutability and changing schema. So having a very fine-grained control over that extensions to the grammar that we needed was important. But the other thing is, one of the key things we've tried to do is to be a thorough implementation of the SQL 2011 ISO specification. So in this version of SQL, which is probably lesser known, so 2016 is the one that gets talked about a lot because they added JSON support. But in 2011, they added these bitemporal table operators. So you could now define a SQL table. When you do create table, you can add a system time column and what's called an application time or valid time column. That's what we use, the word valid time. And yeah, these columns are on the table, but they are maintained by the database, and they have a single invariant, which is that there is no overlaps between the values in those timestamp columns. So unlike your own user provided updated at column, where you're in charge of setting it using SQL, these columns are automatically maintained. And when you make an update into the table, what it will do is it will close the intervals in the previous row and insert a new row with start, and then the end is like end of time sentinel value. And so 2011 specification has these DDL, data definition language constructs for defining these tables. And they also have these period predicates. So you can say like the full range of Allen interval operators, which allow you to ask questions like when was Bob and Carol, when were they working at the same organization together? Or who was working at this organization between these two dates in the past? So these interval operators are fairly fiddly to get right in raw SQL. And also it allows the engine to understand declaratively what that constraint is that you're trying to model, because you have this sort of first-class SQL keyword. And so if you actually look at the SQL 2011 standard, people have done sort of, surveys, reviews of the different databases and how well different ones have implemented it. But very few have really implemented it like thoroughly. And Postgres doesn't implement it at all. I think the only open source option really, there's a couple of extensions for Postgres which do attempt to add it. I think MariaDB has some support. If you want the best possible support, you'd have to look to things like SQL Server, which only has system time support, not application time, and things like DB2 or Oracle, which have various almost standard compliant, but not quite implementations of these things. But what we've not seen broadly, I'd say, is lots and lots of application code using or embracing this version of the standard. And you've got to ask the question why that is. And I think it's because it is too specific or targeted. It says, for this table, I want it to have versioning. And I think that is something which developers want by default. They don't want to have to say, I want this table to have versioning. And part of Rich Hickey's view of these things is that versioning should be ubiquitous. You should be able to say, I want the entire database to have versioning. So why am I forced to, when I create a table, decide that this table needs versioning, but this other one doesn't? Or maybe I decided I didn't want versioning on this table, but now I do, and it's too late and I haven't got the old versions. And so what we've tried to do with our implementation of this specification is make the default SQL experience just storing all the versions. And if you ever need to travel back in time, the old versions are there. And then we have this, I've mentioned two kinds of time. I'll just explain this briefly. So system time is the time that data physically enters the database. So it's the wall clock time of the database itself. And then there's this other timeline, which is essentially like a universal modeled time. And you can use it in different ways. But primarily it's for when you want to backfill information that you've learned from a different system. So let's say you have an enterprise with 2 or 3 databases, and you want to create a fourth database, which can understand a view of what your database, what your business knew in the past. You need to backfill that view of history into your database. And so you have this valid time or business time, which is a curated timeline. And XT basically gives you this for free. So as a SQL developer, you don't even have to think about having these extra timelines. You just write your application as normal. And our thinking there is that this is a much simpler experience for actually using these features. And if you look at how this spec tells you to use these features, it's actually far too complicated. And I think that's been a big barrier to people wanting it and pushing vendors and open source implementers to add these features, because there's some problems with the semantics or the way you think about them. But yeah, we're also excited to just push the design envelope and make these more ubiquitous. And Malcolm raised the example of like garbage collection. It should be something that's easy, that you don't have to think about it.
Yeah, I should just wanted to just expand upon Allen's interval operators or algebra, just to maybe not all your listeners will be familiar, but it turns out there are only kind of 13 different ways of comparing 2 periods of time. One can be a period is definitely happens before another period of time. They can relate to each other in 2 ways. The first period might be before the other period, or the second period might be before the first period. But then they might touch. They might, as the end of one period is exactly the time of the beginning of another period, or they may overlap, or one period might entirely encompass the other period. And so there are these. Turns out there are only 13 ways, and they've been written up. And the difficulty is they all have all these schemes have different names for naming them, and SQL has one naming convention. We've chosen to use the SQL ones. And the second one really is that we're very fortunate that SQL incorporated these bitemporal extensions, because we've had immutability from a long time ago. A log file is immutable. You can open a file for append only, and that's been something that's been around for a long time. You can use an LSM tree, which is a kind of a structure that gives you that same append only, so that everything that you've written in the past Or even like it goes back to the 14th century or the 15th century Medici, the accounting ledger and double entry accounting. The idea that you can't rub things out, that probably goes back to the Assyrians and carving things in stone. However, the interface to access the data is just as important. And what's held SQL databases behind and made it difficult to use SQL to access this immutability has been the interface of SQL itself. So 2011, when it was standardized, that's a great leap forward. You need standardization. And yet it's not that too long ago in the database world. It's moving fast now. But if you compare 50 years, SQL is celebrating 50 years this month. It's not too long ago, and it's about a quarter of SQL's lifetime. So I think this kind of, the interface is very important, and it's not surprising given how long it takes to build databases that not too many database vendors have been able to incorporate these extensions, because these extensions to the interface are actually require a complete rethink to how a database architecture is designed. And that's the challenge. If you're an incumbent vendor, you don't get the chance to completely rethink your architecture too often.
Yeah, I think it makes sense. And I also believe interface is really one of the most important things about a database, because most developers just use the database and they just have this interface for them. And if this interface leaks some of the information, like internal information, it is also not great, because then application developers tend to design something which is not really supported, but the interface leaks it. And I've seen it in some of the databases that they just, for example, Cassandra has this allow filtering, which just allows a developer to just query anything, but it's not really the primary use case they wanted to support. And then to take it back, it's really a terrible thing. So, and there are some other examples as well, but let's try to understand. So I see that XTDB has a SQL interface and it's pretty good, because SQL is easy. SQL is known with everyone, and everyone has been working with SQL since many decades now. How do I get started with XTDB, right? So I want to understand, if I look at a high level architecture of XTDB, what are the components involved, and what am I looking at? What are the big components? And then I would love to understand like how the data flows when I try to insert something. So let's start with the architecture.
Yeah, so we're big fans of reusing things where we can and getting leverage from components. Yeah, historically speaking, we've lent quite heavily on the durability and semantics of the Kafka API. So that's, first of all, quite central, even if it's not Kafka itself, just something which takes away the pain of worrying about the durability and consensus. I'll come back to that in a minute. Another big component is object storage. So we're for a database which wants to store records indefinitely, or certainly large amounts of history, where potentially actually you're only interested in the most recent subset of data most of the time. Occasionally you want to go back into history. It's important to have or embrace sort of the modern storage practices, and the sort of S3 compatible object storage is where we've chosen to place our bet. And obviously you get all the benefits of tiering or transparent tiering from all kinds of technologies which implement that protocol. And then the third real bet that we've placed is on Apache Arrow. So Arrow is, I'm aware some of your previous guests on the podcast have talked about Arrow at length. So I did see you spoke to Andrew Lamb. But yeah, Apache Arrow, for those who aren't familiar, is an in-memory columnar data format. Very good for any kind of analytical queries. And we've actually decided to base our entire data format on that. So we although we are a SQL engine and different SQL engines have their own opinions about types, we've chosen to make the Arrow type system our type system, and we've added some extension types for things like sets or other things that we might care about. But primarily, we're an Arrow first database. So these are the three core technologies. We're also built in the JVM, of course, which I've mentioned because it's primarily written in Clojure. We do actually have a few classes of Kotlin in there as well, for reasons I won't get into, but that's an interesting debate in itself. And the reason we've chosen to embrace the JVM is that's what we're familiar and comfortable with. And I think the JVM is still moving forward. It does warrant some discussion or debate, I think, around the relevance of the JVM in the coming years. But I think for where we are and our target audience, I still think it has a huge longevity, and performance isn't always, or like the last little bit of a performance isn't too big a concern for us. And because we've placed a bet with Arrow, there's always the scope to incrementally over time move elements of functionality out of the JVM and into Rust or whatever you need to do. So those are the key technology pieces. And in terms of the data flow, so when you insert into, in fact, so I should say this as well, we've always had this sort of dynamic quality about it. So coming from Lispers, community of Lispers, we've really tried to make using XTDB as schemaless as possible. Certainly for modern audiences who like MongoDB, this is a good thing. We do appreciate that, though, that there's quite rightly a lot of people who don't want a truly schemaless database, but there are still good reasons when prototyping why this schemaless quality and being able to ingest different objects, different sources is valuable. And this is why I think you see the rise of data lakes. It's because no one really wants to own the database schema truly. It's important to have an engine that can interoperate with different schemas. Yeah, we really lean heavily into things like arrows, union types, which allow different polymorphic combinations of sort of composite types and scalars to live in the same SQL column. So you can have floats and ints and arrays all in the same column. And yeah, what I'm telling you that for is because when you write insert into foo and you provide a big like JSON structure in your SQL, you don't have to do create table. You don't have to declare in advance what the types of those things are. And what happens is we take that SQL statement, and actually if you do it as a prepared statement, we will take that as an arrow data structure and stick that as a record onto a Kafka queue, essentially. And so at that point, it's a durable thing, and we can return to the client and say, hey, your record has been durably saved to XTDB. It may not be validated and processed or indexed by the system, but at least you have a timestamp back from Kafka that says, if you then take this timestamp receipt and ask the XTDB node, have you seen this receipt? And if it says yes, then you can be sure that at least it's seen that record that you put onto Kafka. So this is a sort of an asynchronous indexing process. And so once something has gone onto Kafka, then we can be sure it's durably written, but we still don't know for sure whether that transaction has been committed. So our transactions are asynchronous or non-interactive. So unlike a lot of SQL systems where the importance of multi-version concurrent control and locking transactions, like that's a world that we don't live in. Like we want to be more on this, like you submit a program to the database and it may succeed, it may fail, but you sort of have to rely on because it's linearly ordered, like you put everything into one Kafka partition, you want to do as little work on that as possible, and you don't want to be putting locks into that flow. And so the transaction times, the system times that are coming out of XTDB are monotonically ordered. It's one thread doing the transaction work. And for the kinds of workloads we're interested in, this sort of single writer design is broadly good enough. And if you need more scalability, you can always add more partitions and integrate views of data and things. But really, we're focusing on a single writer here for the moment. And so, so you then have many XTDB nodes potentially all reading from this Kafka queue. And they all have a deterministic state machine representation of what that should look like in an index format. And then these nodes are all racing, so they don't communicate with each other. All the information is going through this Kafka log, and there may be some metadata in there as well about what nodes are connected and things. But these nodes then eventually, say you get to 100,000 rows, and then you save a chunk of data as arrow, and you stick it into, we actually serialize it into the arrow's file format called feather and put it into S3. And at that point, that chunk of data is immutable, and the internal structure of that chunk we can get into in a bit. But before the chunk has been created and sent to arrow, even XTDB can immediately, as soon as it's read the timestamp from Kafka with that recent transaction and it's indexed it can immediately then respond to queries to say, yeah, I've seen this transaction and I've either committed it or not committed it. And we have an API called execute TX, which makes that whole thing synchronous. So actually you don't have to have a asynchronous dance. You can just block until your insert has gone through Kafka through to one or more nodes, and then you wait to see what the result of that is. So that's the life cycle of a single transaction. So we have this row-oriented thing in front of this more columnar-looking thing, and that's very much inspired by Delta Lake, which I think really pioneered this, or at least has done so very openly, publicly. And Delta Lake is the Databricks system for table storage and object storage.
Interesting. So I just want to validate my understanding, right? So I just insert some data. I don't have to like create a table because it's the schema. It's basically schemaless, and when I insert the a row, let's say it has like a couple of columns, so it goes to a Kafka topic, and then that Kafka topic is partitioned based on some ID, and I assume it's like the primary ID or something like the primary key, and then I assume you use Kafka just to have this ordering guarantee per partition, right? So you have, a single writer writing to the same partition for the same key, and then the receiver will have everything in one partition in a linear order or a sequential order. But then when is exactly the index created? When the message is consumed from Kafka topic, it is exactly that time when it creates an index and pushes the data to S3, right?
So just to clarify a couple of things there. So currently we really rely on a single partition. So in a sense, XTDB is not write scalable in the way that you might expect of, like a MongoDB cluster where you have many nodes with separate shards of data. So we really rely on a very strict serial ordering of transactions on a single Kafka partition. As I say, that's currently, I think in future, there is scope for having a partition potentially per table or per database schema in a Postgres sense, I mean. But yeah, currently as things work today, that's the design. And yeah, the main motivation for that, we didn't want to bring in Zookeeper ourselves. Kafka is a very common API, and we didn't want to be inventing our own durability semantics. Like, we want to focus on where we think the value is for the engine rather than just reinventing some infrastructure that already exists. But in theory, in principle, at least, if you want the absolute lowest latency, then you probably have to bring that consensus piece in-house, in which case, yeah, maybe Kafka is quite heavyweight for what we're needing it for. However, for a lot of the infrastructure, it is available. And in our experience, in our user base so far, it seems to be reasonably common, or at least there are enough managed services and things these days to make it not an issue. And what was the other thing you said? I forgot what that was.
It's about the index. When the message is written to Kafka, there are these XTDB nodes that are consuming from Kafka, right? Is the index created once it is consumed from the Kafka topic, or there is a separate process that does that?
Yes. So yeah, as soon as something is consumed, it is available for other for queries hitting that node to view. It's not written out to S3 immediately. We accumulate enough novelty in the system such that these chunks are, let's say, efficiently sized. Because when you have columnar data, especially, so yeah, all of this data, although we take rows in, we split it up into columns, or arrows naturally split up into columns, and then in a columnar format, you can get more compression and things can be scanned over much more quickly or aggregated much more quickly. So that's why you want it in that format. But in order to get a sufficiently large chunk, you need to wait for enough transactions to accumulate. You wouldn't want to flush to S3 too often, otherwise you're not getting the right granularity for the storage. So I guess as a rule of thumb, you might want to save 100 megabytes up to S3. You would not be saving like a couple of kilobytes.
Yeah, that does make sense. And since I have the message in Kafka anyway, so the durability is covered. And then if I somehow I fail to do something after that, so the record is still there. So that makes sense. And then the read queries are blocked until the message is consumed from Kafka and it's written to S3, right?
Depending what you want to read, if you want to read the current state or the state of the database just after you've transacted or done a change to the database, that's true. But if you're prepared to see an old version, maybe 5 seconds ago, of the database, you're not interested in the novelty of the change, then version of the database is available straight away. And not only is it available straight away, it's available on any number of nodes that you choose to add to the cluster, so that this very principled way of dividing reads and writes allows you to, with the cost of not having distributed writes, if you have a single writer, but you can have distributed reads, or you can have, or rather, you can have partitioned reads, and you can, and there's no limit because you've got that, you've got every single version of the data available to you, and you can decide to almost like copying files would work as well, where you can just copy some files from a disk and then you can onto your laptop and work on them on your own without anyone being disturbed in the cluster. So you have that property of when things are immutable, you get the opportunity to copy them. This is exactly how Clojure used to work. When things are immutable, you don't have to lock things. You can copy them and process them and do compute on them, knowing that they're not going to change.
Yeah, just to add to that, I think you have this idea of read transaction, and all we're doing in this architecture is saying read transactions don't need to be these stateful things which impose work on the server or on the transactional workload. You can have these unbounded read transactions which operate on stable snapshots, and the snapshots could be as of half an hour ago, as of yesterday, as of last week, and the semantics of the system is much more similar to this common thing about event sourcing and command query responsibility segregation, where people want to separate reads and writes. And that's what we're doing here, is giving you those semantics, but in a veneer of SQL. So rather than going down the road of trying to make XTDB look more like Postgres, we're very much on the side of what are the architectural things people want from their database systems, and let's implement that rather than interactive transactions.
Yeah, that does make sense. And so I have some more questions on the write path, but let's get back to the reading part, right? So I have executed this insert query and then I want to read some data. Now, it can still give me like a old snapshot version, let's say, I don't know, a few seconds ago. And then how do I know as the consumer that what version I'm getting served? Is it the latest one? Is it based on the snapshot? So how is that information exposed to the user?
So you can be sure that when it's all based on the system timestamp essentially. So you have one microsecond precision timestamp, and when you run a query, you're always running it in the as of a timestamp. And the only way you can be absolutely sure that the system hasn't progressed since, and you're not reading some stale data, is to send your read as a transaction through the Kafka queue. So if you need absolute guaranteed latest, you essentially have to put that onto the write path, which then has some impact on the transactional performance. But the benefit of doing it this way is that you can have infinitely scalable horizontal read replicas that are just a fraction of time behind, but they are able to cooperate consistently because all they need is a timestamp to coordinate. There's no expensive locking or complex node-to-node interactions to determine which versions of things they're looking at. All you need is a timestamp to have consensus and consistency.
Okay, interesting. So now I have inserted some rows, for example, right? And then it is indexed. And I also have a document, like a small JSON. It has a primary key and then it has a JSON document, for example. Is the index created only on the primary key or also the internal, like the nested structure of the JSON?
Right now we have one primary index, which actually also is a covering index. So it is the thing that decides the layout of all the columns, but it is indexed on the primary key. So every table in the database has an ID column, and you can't change that, right? It's just a fixed ID column. And the reason we have this like one main index is it's a temporal index. And this is what allows you to filter the database efficiently as of different points in time. And it's also essentially important in this LSM structure we maintain in the object storage, which over time is ordering by recency. So more recent things will live in like a hotter area of the database. And if you're making updates to rows, those older versions like drift off into the part of the LSM structure which doesn't get touched, and that can be then benefiting from the tiered storage semantics. So that is the main index. Anything beyond that, currently we have a vectorized columnar engine which is optimizing for these sort of snapshot-based reporting workloads that we seem to be coming up against most on our sort of I want to query the past requirements. And that engine is operating on the raw columnar data plus your min-max and some Bloom filters at the columnar level. So there aren't B trees involved or other sorts of dedicated secondary indexes. However, we may add support for that, regardless of whether that not an index. Currently, you can query deeply nested structures in your documents, and it's not JSON in a string. We actually map your document structure directly into arrow types under the hood. And so the engine is compiling the polymorphic Java required to dig into those deeply nested arrow structures and aggregate over them very quickly, as quickly as possible, in a columnar way. And for many workloads, that's acceptable latency. But there definitely is a trade-off there where we want to be a good citizen in the we're going to store lots of history space, but we also do want to be practical for people to build real-time applications on. So things can't be too slow. And so that's the balance we're trying to figure out still with our designs. But yeah, it's very likely we will add secondary indexes in the near future.
Okay, that's interesting. And you also answered one of the questions that I had, since we are talking about immutable data, and there may be updates and changes happening to my data. So you might have a ton of data for each key, for example. So how do you maintain the storage? But I think you explained how the tier storage can be used, and the cold data, or let's say the older data, can be moved to like something which is way cheaper, and hot storage can only store the recent versions. How do I, as a user, define what is old enough to be pushed to cold storage and kept in hot storage?
So I actually think this notion of business time or application time or valid time is one potential solution to this. And so we're not the first group of people to think hybrid transactional analytical workloads are a good idea, or isn't there something in this space of wanting to have interactive transactions, build an application, but also be a good long-term store of data, not having to write loads of ETL jobs to move data from one place to the other. But one of the constraints of doing that is knowing how old is something before it's no longer relevant, and how should an application declare to the database that something is no longer relevant. And so we have this timestamp field, which is essentially like a deleted app. So when you say something is no longer valid, it is what you can actually write regular delete statement in SQL, and it will close the valid time period for the row. And at that point, the database then has this hint that actually maybe this is no longer required. And I think this semantic that valid time offers is potentially actually an important key to enabling this HTAP, hybrid transactional analytical processing vision, because the application, I think, does need to hint in some way that something is historical. Yeah, so that's my main response. And I guess you did mention about the storage of history, and a common question I get is what you talk about by temporal, and how is temporal different to time series? And I think the main thing is this attitude to the semantics of having many versions. So in a time series database, you just assume that each entry is a new version, but that doesn't give you any capability to say that these versions were wrong. And so the difference really is around the ability to curate the timeline and to say, between these two time periods, we actually want to change these values. They're all rubbish. There's a mistake in the integration. We need to replace that period of history with the correct versions. And so that's what the temporal part is all about. It's about curating the timeline. And yeah, as a consequence of that, I think the engine then has the capability to understand from that timeline what is actually important to keep in the hot set, keep in RAM, or push out to object storage and forget about. And I think that being a ubiquitous part of the schema and not locked up in the data model is actually quite an important design choice. Yeah, I think if we can prove that it's a good idea, I wouldn't be surprised if in a few years you see all the other data lake vendors want to scramble around to implement valid time because they see it as a way to differentiate between the hot set and the cold set.
Okay, interesting. I do think that probably for some of the cases, this time field cannot be the only one factor that decides when to move something to the cold storage, right? Because I'm just trying to imagine, like for certain tables, I don't know, they are generally very like slow moving data. It's not updated frequently, and the table size doesn't grow crazy. So for those, even if those table has data like really old, like a year ago or something, but they still might be required for some processing, like being in the hot storage. Are there any other parameters to decide when to move something to the cold storage, like data size, number of updates, or the table size, for example?
I think there's a counter force in the architecture, which is having caches, and the more often something is queried for, the longer it will live in a cache. And that is the the answer to that problem, I think. Or generally should be. And maybe there's thoughts there around the importance of workload prediction or the ability for the engine to learn the pattern of the data. And that's certainly something I think is really not talked about enough at the moment in this current AI hype cycle. A lot of focus is going on generation of SQL, and I think that's an exciting area. But I saw you had Andy Pavlo on recently talking about his work on using AI within the database to manage configurations and tuning. And I think that is exactly the place to be focusing. I'm not sure that work directly is relevant to what I'm discussing because that's focused on like Postgres optimization. But in general, the application of AI within the database for doing things like managing join order and compression is a huge area as well. And that kind of is also part of the same problem. It's how does the engine know to invest a little bit more CPU resource to develop a more efficient compression? And really that's a function of how much does the engine think that this piece of data or this part of history is likely to be queried again. And so that needs to be factored into the compression. So I would like to think that XTDB can be a good platform for building out these sorts of interesting machine learning techniques and systems, because I think we are generally seeing a lack of take up in the open source database world of just the torrent of good ideas coming out of academia on applying machine learning into databases.
Yeah. I think I want to jump back to the right path because I had some questions there. So as you mentioned, there is like one Kafka partition and I am writing all my transactions into that partition, and then there are nodes consuming and doing the necessary storage thing. How do I maintain like isolation when it comes to having different transactions? Because some of the transactions maybe, I don't know, they're really heavy in terms of some of the keys are really updated or deleted, or some changes are coming up in some tables very frequently as compared to the other tables. So since I have one partition, how do I make sure that there is no sort of noisy neighbor problem when I talk about such data?
Yes, so that's very much down to the application to not bombard the transaction with large blocking transactions. So if you have a very long running migration job or something like that, you would want to break that down in a way and present that to the database. Lots of small incremental changes. Yeah, so that's the answer as the end user. The overall design we've picked is, as I've mentioned, very inspired by Datomic, which was another closure database. But actually, Jepson, the Carl Kingsbury and co., they recently released some analysis on Datomic and described its execution and transaction model. And I think for anyone interested in this design, it's a worthwhile read because it's very neutral, although ironically, Jepson's also written in Clojure. But it really looks at Datomic from this lens of the serialization and isolation properties as defined in academic thinking. And we really follow that. So the isolation is like 100% because there is only ever one transaction executing at a time. The transactions are accretions of data rather than these things that interleave from multiple actors or observers. It's like you send some data to the database and that's it. That's the vision. If you have a very long running transaction, you can model that out in many different ways. You could put something in front of the database to assist with that, but ultimately it's making the database do less. And so that's the guiding architectural principle. And so maybe that means the application should do more, but then it probably means the application should do more, right? The database can only be so intelligent. And I think this is the problem with all kinds of locking schemes and why people move workloads eventually out of, they might get Postgres to scale up to a certain amount, but then they'll pull out parts of it and shard it and treat it differently anyway, because the locking model or this read-write model is fundamentally flawed in some way. That's a bold claim, and I'm not sure I have a proof written down of exactly that, but that's certainly the school of thought we're in and following.
I think it comes down to what you want a database to do for you. In the old days, and from working with Oracle back in the kind of 90s, but also Postgres, what a database is doing is really just allowing lots of clients to connect to it and update the current status of the world, how you've modeled it. And that's the only thing that matters. And history is unimportant. The only time that history might be captured is if you do an extract from the database or a backup and you load it into a different database. But that is something you have to do out of band. If you want to capture and model history, you're really having to simplify the past as a sort of series of discrete frames that are happening one after the other. Of course, the universe doesn't work like that, but what these systems are meant to be a simplified approximation of what we want to record. And it really does simplify things if you say that you can go back in time in a database and every change is a discrete change happening one after the other one. Because if you want to understand what happened, you then have a story of events. You don't have the problem of having to think in your head, these events might have happened in a different order. You know that you've got an agreement of what the order is, and therefore you can recompute exactly, precisely what a particular state is at a given time. And that is a massive simplification. If you want to have if time is, and the history and the past is important to your application, and in financial applications it often is, and you want to account for those things, and perhaps you want to query across different time dimensions. If that time dimension is important to your application, then modeling time as a discrete set of events is a very useful idea. And therefore, it very much, we don't have to use Kafka, but we have this idea, and Kafka is absolutely perfect for this kind of modeling, but where you can record each transaction one after the other. So you could do that in a log. And in fact, XTDB doesn't depend on Kafka. You can store this kind of idea in object storage or in memory, or there are other options to the database. But it really does come down to how important the time dimension is to your application. And therefore, if you are going to capture that time dimension, you're going to lose a little bit of the performance that comes from parallelization that many clients can all. And parallelization is achieved in databases by just allowing as much as possible each actor to do what they like, as long as they don't step on each other's toes. So there's a little bit of contention, a little bit of locking, just to avoid two actors hitting the same row at the same time. But apart from that, everything's optimized for performance, for getting as many transactions throughput through the database as possible. But the trade-off there is that you lose the opportunity to track time precisely. So it really is a question of trade-offs, and as most things are in databases. And that's why there's not just one database to suit every workload. And it is that these decisions are full of trade-offs. So we are really only building a database for people who are interested in the past, as well as the present and indeed the future, if you're building something for scheduling, who are interested in that time dimension.
It does make a lot of sense. And as you said, it's all about trade-offs, and understanding those trade-offs is really important. And that's when the general purpose databases are so popular, that you don't really have to think a lot about different stuff, because it's general purpose. It will work for you. But then there are times when it doesn't work for you, and then you need something very specialized in that particular domain, like time series databases or analytical databases. And this is interesting. And moving to a little bit of the user experience side, so I know I have to write SQL. What kind of SQL support? It is like SQL, or it is like compatible with some standards, as you mentioned, for example, Postgres. I was reading the document, and it mentioned that it derives some ideas from Postgres, but it's not exactly Postgres SQL, right?
Yes, so where possible, we've actually paid for the copy of the ISO standard, and we're sort of trying to follow it to the letter. In many places, it's an enormous thing, but yeah, we've been wanting to follow the standard where possible. If the standard doesn't cover something, then look to Postgres as a secondary source. So that's that's been our general vision of how to implement SQL. But one of the first things we actually made sure we had working was the SQLite logic test suite, which is, I can't remember the exact number. It's like hundreds of thousands, maybe millions of individual queries. It's all generated queries with very complex logic in the select clauses or many joins, and really is a good thorough test of a subset of the SQL engine. And so we've gotten that passing, and that itself requires like some level of compatibility with SQLite as well. Yeah, those have been the biggest sources. And then we also have TPCH being a big guiding influence in our benchmarking and understanding the performance profile for what we're aiming for. So those are some fairly gnarly queries that you need to decorrelate in order to make work efficiently. So we use those as an exercise for our planning and optimization as well.
Yeah, interesting. Let's talk a bit about the deployment. I as a user, if I want to use XTDB, what are the different offerings I have? And how do I get started, deploy XTDB, and what kind of dependencies do I need? For example, I hear Kafka and S3. So how do I connect all these pieces together and get XTDB up and running?
So we have a CloudFormation template, which is probably the easiest turnkey way to get a production-worthy setup running. So that will spin up a Kafka cluster and configure a ECS node with the right configurations to connect to the Kafka cluster and an S3 bucket as well. So that's like a minimum viable production deployment where you put data in and you can be guaranteed it's going to save durably. And if you kill the ECS node or something happens to the ECS node, or there's a bug in our version of the database, then at least the data is there durably. And it's definitely a big advantage for us building an immutable database is that the barrier to us getting it wrong is a lot lower because we're not mutating things. So if there is something that goes wrong catastrophically with XT, it actually doesn't affect the data at all because we've never touched the previous versions. So that's definitely an interesting implementation angle. But yeah, if you don't want to get embroiled in AWS configuration, then the other option is just to download the Docker container where it will spin up a port on localhost 3000 and you can send SQL statements over HTTP. We've also been working on a Postgres wire protocol compatibility module, which means you can send SQL over PSQL or other Postgres compatible tools. So that's another interesting area of conversation if you want to go there. So yeah, you can connect to your local Docker container. It's just running in memory, but it gives you a feel for what the SQL semantics are, how the immutability works. We also have a mode of using XTDB in process on the JVM. So if you are coming from Kotlin, Scala, Clojure, Java, then you can actually run queries very efficiently directly in process without having to go through a network hop, and potentially even benefiting as well from Arrow's in process communication. So you don't have to do any sort of deserialization. And because of this immutability, and this is one of the reasons XTDB is quite exciting to part of our audience, is its snapshot-free semantics, or the very, very cheap snapshots, such that you can run complex queries and break up your query logic across many different queries, all running at the same point in time, all in process. More like how people like to think about SQLite, building apps against SQLite is getting very popular these days, but with this very easy ability to run against a single snapshot where results aren't tearing underneath you. So that in-process API is also there. But I would also say that we have a playground environment as well, which if you don't want to download anything, you can try XTDB. Just go to play.xtdb.com and start writing some SQL. And we have a Lambda which fires up per request, which is another thing we could talk about. How to get XTDB running is in 62 milliseconds and starting up and disappearing again. But yeah, those are different ways you can use XT right now.
Yeah, sounds pretty good. I like the playground approach. I don't have to do anything. I just connect to something and run some queries, and it's all clean state for me if I have to quickly try something and what kind of features are supported. Whenever I talk about databases, and since we are talking about an immutable database, I'm specifically interested in understanding in the real world there are some use cases because of some compliance reasons that a user is asking me to delete some data, that delete all my data, and I get a request. How do I do that kind of stuff with XTDB? Is it possible to delete data like for a particular user?
Yeah, so unfortunately the word delete was already taken in the SQL standard, so we had to find another one. So we came up with erase. So you can erase a record, and what that will do is actually eventually compact through this LSM primary index structure, and it'll insert tombstones and prevent those records, all the records, from being read, and then eventually they'll be removed from object storage. So yeah, we have this erase command which works like any other insert, select, or update statement in SQL. And yeah, that's definitely good. A lot of people might be tempted to reach for it as a space reclamation feature. I would say that's always an anti-pattern. It really is just for those exceptional circumstances where you do want to comply with some regulatory demand. Or another thing that's get asked about quite often is, can you have a retention window, say automatically raise after 7 years or something like that? We haven't implemented that currently, but I think that's definitely one for the roadmap, because going into a scenario where you're storing everything, people want to actually codify and implement these data lifecycle policies as easy or simply as possible. And what better place to do it than the Immutable database?
After you've said this, I think I like erase keyword better than delete. It's much better. Cool. So I think we have covered like the high level understanding, things are working internally as well. I'm still curious, like what kind of, and I guess you briefly explained this as well. What kind of use cases are the best fit for using XTDB?
So I think people have been dreaming about this time travel capability for many years. And actually one of the biggest researchers who worked on it for the longest, Richard Snodgrass, was writing back in the 90s in the context of insurance, where they had an insurance client who wanted to keep track of who had bought properties and when. And if you realized you'd digitized some information wrong, you'd want to go back and say, oh, actually, no, it wasn't Sue living in property A, it was Bob. And you need to correct that in a way that's like a rigorous model. The bitemporal model, as Snodgrass coined, was born out of that kind of requirement. It's certainly any sort of environment where people need to have a forensic look at what's happened and when, like who knew what and when. As the global financial crisis proved, became very important for banks and financial organizations, hedge funds, etc., to keep much better records so that they can be accountable and easily prove to regulators and auditors the state of the world. And so that we found that this is where our exposure to this idea even came from, is working in these spheres where there's a huge importance attached to the decisions that are made. And what the bitemporal model allows you to have is confidence about the state of the known universe at that point in time that a decision was made. All the reference information doesn't have to be denormalized and stored as a JSON blob next to the decision. It's like you can be very confident that a decision was made and you had the full context around that decision, and you can query and inspect that. And so as regulation increases in different industries, I think like things like manufacturing, telecommunications, energy, these sectors will see increasing regulatory requirements, which will point more and more in the direction of the bitemporal model. And Richard Snodgrass was thinking about all this in the 90s when hard disks were too expensive, I think, to make it a reality. But now we have the tools and the language, I think, to discuss this appropriately. And anyone working in those sorts of projects where, they're spending forever and a day tweaking audit tables and triggers to build an immutable system should really take a look at the bitemporal model more seriously and think about if it applies.
Yeah, I think it's a profound potential to organizing data around a timeline. And I think it's difficult to really grok how much of a difference it makes. And I think it's only, I think for developers, I would use the example of Git, because we used to save changes to a file system and an external share, and used to try to manage, to ask the question, well, what piece of code was running where at what time and why did it go wrong, and to actually go and do the ad hoc forensics and to try and work out what snapshot was being used. But the Git model has really, I'd say, revolutionized software development lifecycle, because we can point to a particular commit, and we know that there is a linear ordering of commits because each commit, because of the way that Merkle trees work, each commit is a sort of assigned derivative of the change, a derivative of the previous change. So it really is that time sliced frame by frame model that I talked about that all data should have. But just by looking at the quite profound advantages to the software development lifecycle that something like Git has offered, it has revolutionized reuse, the whole GitHub experience, or GitLab, Bitbucket. And I don't think any developer wants to go back to the old days. And so many users in the world haven't been exposed to the advantages you get where time is just built in and is just a given. And so developers instead have to recreate these kind of half-baked version control systems in their applications to give people the idea of an undo or a record that can be resurrected. And these are very primitive ways of managing time in an application. And I think that excuse the pun, but the time has come. We have the resources to properly manage time in data. And I think whether XTDB will be the product or the database that brings this into the mainstream, or some other product will do, and hopefully some developers out there might be inspired by the XTDB design and copy it, and I hope they will be, because I think this is a kind of one of the undiscovered gems that is still out there to be discovered, and it will absolutely simplify many of the IT systems that we have today, and for the benefit of users. Simpler systems are better systems for users. I hope that this will be discovered by a great number of people, and that we start factoring in time into our designs.
Absolutely. And then it's not just about implementing once. Like if I have to implement some version control in my application, and then I have to do that again. So it's not like reusable model. I have to re-implement and probably adjust a bit for the other use case as well. And then someone tries to copy them. They have to like keep doing it to get that done. And there can be like different problems and different challenges to each one of those. So why not use a database that specializes in that and makes it a first-class citizen? So I really like this idea. In the interest of time, we have to end this amazing session, but I think we have covered a lot of ground. And for folks who are more interested in learning about XTDB and what you're going to release in the coming future, what is the best way?
You should be able to head to xtdb.com, and the information architecture should take you to the right places, but always feel free to reach out to me personally. I'm at RefSet on social media, and always keen to chat to people that are curious about these topics.
Awesome. So thanks a lot. And I'm looking forward to releasing this episode, and looking forward to what our viewers think and what their questions are. So I'll add the necessary details in the description of this podcast. And yeah, so thanks a lot and have a good one.
Wonderful. Thank you.
Thank you, Kaivalya.